So I was standing in line for coffee this morning, and I'm just, trying to get a standard drip coffee,
Just simple stuff.
the simple stuff. And I'm looking at the menu board, and it's a dissertation. It used to be you had two options, regular or decaf.
Right. Maybe a dark roast if you were feeling wild.
Exactly.
Mm.
Now it's oat milk, macadamia nut blends, nitro-infused cold brews, distinct acidity profiles. I mean, you practically need a degree in organic chemistry just to order a drink.
It's the paradox of choice. We're seeing the same thing happen in fitness, too. Remember when going to the gym just meant, I don't know, running on a treadmill for 30 minutes?
Yeah.
Now, if you aren't doing HIIT intervals followed by macronutrient timing and intermittent fasting,
Mm-hmm.
are you even working out?
Right. It's this explosion of complexity. We've gone from simple utility to this high maintenance specialization. And the reason I bring this up isn't just to complain about lattes.
Oh, my God.
We could do a whole deep dive on that, but it's because this is the perfect analogy for what's happening in tech, specifically with artificial intelligence.
That is a great comparison. A few years ago, for most people, AI was just robots.
Automation.
Yeah, or automation. It was the black coffee era of tech. Simple, singular terms.
And now we've got the nitro-infused oat milk version. You can't open a tech article without getting hit with a wall of jargon, machine learning, deep learning, LLMs, generative AI, neural networks. It's overwhelming.
It is. But just like that coffee menu, the complexity signifies capability.
Hmm.
We aren't just automating simple tasks anymore. We're mimicking cognition. But to navigate that, you need to know what you're ordering.
Which is exactly our mission for this deep dive. We've pulled together a massive stack of research and articles to decode this lexicon. We aren't just going to define the terms.
No, we're going under the hood.
We are. We're breaking down the big three: machine learning, deep learning, and NLP. Then we're going to head into the kitchen, so to speak, see how these models are picked up, and finally look at the cutting-edge stuff like reinforcement learning.
I like the roadmap. It's essentially a crash course in being fluent in the modern world.
So let's start with the foundation. The term that gets thrown around the most, and usually incorrectly, is machine learning. Now, I've always understood ML as the broad umbrella term, but what's the actual difference between a standard computer program and machine learning?
That's the fundamental question. Traditional programming is explicit. You, the human, write a rule. If the user clicks this button, then open this window.
Okay.
Or the temperature's above 75, turn on the fan. You are hard-coding every piece of logic. The computer is just following orders.
Right. It's a dutiful soldier, does exactly what it's told, nothing more.
Machine learning completely flips that. Instead of programming the rules, you feed the computer data, and usually a lot of it, and the computer figures out the rules itself. So you aren't telling it how to do the task. You're telling it what the results should look like and letting it derive the path to get there.
So to use a real-world example we're all glued to, streaming service recommendations. In the older days, a human might have programmed, if a user watches action movie A, suggest action movie B.
Correct. That's a rules-based system. But that doesn't scale, right? You can't write a rule for every movie ever made.
No way.
Modern machine learning looks at the data. It sees that you watched a 90s action movie, you paused it 3 times, but you finished it. Then it sees you clicked on a sci-fi thriller the next day. It compares your behavior to millions of other users who did similar things.
So it's essentially saying, hey, a million other people who like Die Hard also really enjoyed The Matrix, so statistically you probably will too.
That's it. It's purely probabilistic. It's finding a pattern in the noise that no human could reasonably code by hand. That is machine learning in a nutshell. Algorithms that improve automatically through experience and data.
Okay, so that's the umbrella. But then we have deep learning. And I feel like this is where the marketing hype starts to blur the lines. Is deep learning just extra strength machine learning?
In a sense, yeah, you could say that, but the mechanism is really different. Deep learning is a subset of machine learning that is, well, it's inspired by biology. It uses something called artificial neural networks.
My brain analogy.
It's a useful analogy, even if it's not biologically perfect. Think of it this way. A standard machine learning model might look at a spreadsheet of housing prices and find a simple linear correlation. More square footage equals a higher price.
Symbol.
Deep learning is designed to handle messy, unstructured data like images or audio or text.
Because an image isn't a spreadsheet. A picture of a cat is just a grid of colored pixels.
Exactly. And this is where the deep part comes in. It refers to the layers. Imagine a neural network as a series of filters stacked on top of each other. The very first layer might just look at the raw pixels and identify edges. where a light pixel meets a dark one.
So layer 1 just sees lines and curves, nothing more.
Right. Then it passes that information to layer 2. Layer 2 combines those edges to identify simple shapes, a circle, a triangle, a pointy ear.
Okay, I see where this is going.
Layer 3 combines those shapes to identify features, an eye, a whiskery snout. This goes on and on through these hidden layers until the final output layer says, there is a 98% probability this is a cat.
That makes the deep part make so much more sense. It's a hierarchy of complexity. It's building understanding from the ground up, pixel by pixel, layer by layer.
And that's why it requires so much
It's computing power.
Exactly. Each of those connections between the layers has a weight, a mathematical value representing how important it is. When the model learns, it's just adjusting those millions, or sometimes billions, of weights until it gets the right answer consistently.
So when we hear about AI beating grandmasters at chess or Go or even identifying tumors in X-rays, that's got to be deep learning, right?
Almost exclusively, yeah. I mean,
Yeah.
those problems are they're way too complex for simple rules. They require that layered, that hierarchical abstraction.
All right, let's pivot to the second pillar of our breakdown. We've covered the visual and the analytical, but what about the conversational? We're talking about NLP, natural language processing.
The linguist of the AI family.
This is the tech that powers all our smart assistants and chatbots. But again, I think we tend to anthropomorphize this. We say the AI understands what we said, but it doesn't really understand English, does it?
Not in the way you or I do, no. It doesn't have a concept of meaning or intent in a philosophical sense. NLP converts language into math. It breaks down text into tokens, which can be words or even parts of words, and turns them into vectors.
Vectors, so numbers in a multidimensional space.
Right. Imagine a massive 3D map. The word king and the word queen would be located very close to each other on this map because they appear in similar context.
Uh-huh.
The word apple might be close to pear in one direction, fruit, but also close to iPhone in another direction, tech.
So when I ask my phone, what's the weather,
Mhm.
it's not looking up the dictionary definition of weather. It's analyzing these vector relationships.
It's analyzing the probability of what response usually follows that sequence of vectors. It dissects the syntax, the grammar, and the semantics, the meaning, to predict the correct output, whether that's generating an answer or, say, translating English to Spanish.
Translation is a great example. I remember those early translation tools. They were hilarious because they translated word for word. You'd type in a metaphor and it would just come out as complete nonsense.
That was the old rules-based approach.
Huh.
Modern NLP looks at the whole sentence or even the whole paragraph at once. It captures the context. That's why you can yell at your smart speaker to set a pasta timer while music is playing, and it can isolate your voice, convert the sound to text, parse the meaning, and execute the command.
It's seamless now, but the math behind it is just staggering.
It is.
Yeah.
And that segues perfectly into how we actually build these things. We've talked about the concepts, but let's go into the kitchen.
I love this analogy from the research material. It really clarifies the terminology confusion I see all the time. People mix up algorithm and model constantly.
It's the most common mix-up. The source material uses baking, which works perfectly. Think of the algorithm as the recipe.
Okay, the instructions. Preheat oven to 350. Mix flour. Add eggs.
Exactly. The algorithm is the code, the mathematical architecture. It's the potential to learn. It's just a piece of paper with instructions on it. You can't eat the recipe.
And the data is the ingredients then.
Yes. The flour, sugar, eggs, chocolate chips. In our world, this is the big data. Terabytes of text, millions of images.
So you take the recipe, the algorithm, you mix in the ingredients, the data, and you put it in the oven. That time in the oven, that's the training process.
Spot on. Training is computationally expensive. It takes time, energy, massive processors. The computer's just churning through the data, adjusting all those weights we talked about, trying to minimize its errors.
And when the timer dings and you pull it out,
Yeah.
that's the model.
The model is the cake. It's the finished product. When you use an app or talk to ChatGPT, you aren't using the training algorithm. You are using the model, the static, trained system that is ready to serve predictions.
I think that distinction is so helpful. The algorithm is the method, the model is the result. But I want to stick with the ingredients for a second. We hear the phrase garbage in, garbage out a lot.
It's the golden rule of data science. If you use spoiled milk, you get a bad cake. It doesn't matter how good your recipe your algorithm is.
And the source material really highlights bias here. And I want to be clear, we aren't talking about political correctness. We're talking about statistical accuracy. If your data is skewed, your model is broken.
Precisely. It's a quality control issue. If you train a facial recognition model mostly on images of one specific demographic, it physically will not recognize other demographics as accurately.
Right.
It's not choosing to be biased. It simply hasn't seen the data.
Yeah.
It has a blind spot because the ingredients were lacking.
So verifying the data set is just as important as writing the code.
Arguably more important in the modern era. You can have the best oven in the world, but if you put in mud, you get a mud pie.
Now, you don't just bake the cake and immediately sell it. You have to taste test it. The research uses a great school analogy here for the development lifecycle: training, validation, and testing.
This is what I call the academic career of an AI. Training is practice. It's the daily homework. The model looks at the answer key, it guesses, gets it wrong, and corrects itself over and over.
Millions of times.
Millions of times.
Yeah.
That's the heavy lifting. Then comes validation. The midterm, you could say.
The midterm.
Yeah, or maybe a mock exam. The developers pause the training and test the model on data it hasn't seen yet, just to see how it's doing. They use these results to tune the settings, like adjusting the temperature of the oven.
Okay, so fine-tuning. And finally, testing. The final exam.
The final exam. And the stakes are high here. The testing set is data the model has absolutely never seen before. It's crucial because of a problem called overfitting.
Overfitting. Is
Yeah.
that like cramming for a test by memorizing the textbook word for word?
That is the perfect description. If a model overfits, it has memorized the training data perfectly, but it can't generalize to new things. It knows that this specific picture of a golden retriever is a dog, but if you show it a poodle, it has no idea.
So it's a parrot, not a thinker.
Exactly. The final exam proves whether it actually learned the concept of dog or just memorized the photos it was shown. If it passes the final, it's ready for deployment.
That life cycle training, validation, testing it really highlights that this is a rigorous scientific process, not just some magic button pushing.
It has to be.
So we've baked the cake. Now let's look at the fancy stuff on the dessert menu, the cutting edge. And the term of the year is clearly generative AI.
It's the shift from what we call discriminative to generative. Traditional ML, like our Netflix example, is discriminative. It classifies things. This is a comedy. This is a cat. This is spam.
It puts things in buckets.
Exactly. Generative AI creates new things. It doesn't just find a cat picture. It synthesizes a new image of a cat that has never existed in reality. It's predicting the next pixel or the next word to construct something entirely novel.
And the power here, as the source points out, is in the prompt. It's democratized creativity in a way. You don't need to know how to draw to create a logo. You just need to know how to describe it.
It's a force multiplier for workflows, writing code, drafting emails, brainstorming marketing copy. It's moving from search, which is finding what exists, to generation, creating what you need.
But there's another type of learning that I find even more sci-fi: reinforcement learning.
Ah, yes, RL.
The source uses the robot analogy, which is just fascinating.
Reinforcement learning is distinct from everything else we've discussed. In standard ML, you give the computer the answer key, the labeled data. In RL, you don't give it any data, you just give it a goal.
Like, win this game of chess.
Or walk across the room without falling. The agent explores the environment. It tries a random movement. If it falls, it gets a negative penalty. If it takes a successful step, it gets a positive reward.
So it's essentially a toddler. It stands up, wobbles, falls down, cries, tries again.
It's trial and error on steroids. It runs through this loop millions of times in simulation. Eventually, it figures out strategies that humans never even taught it. It learns that, oh, if I bend my knee at this angle, I stay upright. It's deriving physics from scratch through pure experience.
That's fascinating because it allows for solutions we wouldn't think of. If you tell a robot, go to the door, it might figure out a way to run that looks bizarre to us, but is mathematically the most efficient.
Exactly. It optimizes for the reward regardless of convention.
Which brings us to the final and maybe most critical point in our research stack: explainable AI. Because if these systems are learning on their own, doing millions of calculations in hidden layers, do we actually know why they make the decisions they make?
That is the black box problem. With a deep learning model, you have billions of parameters. If the AI denies your loan application and you ask why, the engineer might look at the model and just see a mess of floating point numbers. They might not actually know which specific factor tipped the scale.
That's terrifying in high-stakes fields. Medicine, finance, criminal justice. Computer says no isn't a good enough answer.
It's not, and it shouldn't be. Explainable AI, or XAI, is a massive field of research right now. It's about building tools that force the model to show its work. I denied the loan because the debt-to-income ratio combined with recent credit inquiries. We need that transparency.
Trust requires understanding. If we can't audit the decision, we can't really trust the machine.
And we shouldn't. The source explicitly states that as complexity grows, our demand for explainability must grow with it.
So we've gone from the coffee shop menu to neural networks baked a cake and watched a robot learn to walk. It's been quite a journey.
It really highlights that AI isn't one thing. It's a collection of tools, ingredients, recipes, and appliances that come together to do very different jobs.
And for you, the listener, the so what here is pretty direct. You can't afford to treat this as magic anymore. You have to understand the menu.
Right. You don't need to be a data scientist, but you need to know the difference between a discriminating model and a generative one. You need to know that data bias is a real technical thing. The advice from the source is just to stay curious. Experiment with the tools, write a prompt, see where it fails.
Get your hands dirty in the kitchen.
Exactly, because this technology is powerful, but at the end of the day, it's a tool. And tools are only as good as the hands that wield them.
I want to leave everyone with a final thought from the research that really stuck with me. We talked about explainable AI, this need to know why.
It's the crucial link.
Here's the question. If we reach a point where the AI is so complex that even with explainable tools, the reasoning is beyond human comprehension, can we still use it wisely? If the why is too smart for us to understand, are we still in charge?
That is the ultimate question of control. Do we trust the results, even if the process itself is invisible?
Something to think about while you stare at that coffee menu tomorrow morning. Thanks for diving in with us.
Always a pleasure.